And this is still a good kind of chalk on the meeting. The other kind of chalk is chalk I get in a Japanese restaurant. All right, so identical particles. This can be a confusing subject. And I think the clearest treatment that I know of is in a book by Cohen-Tanucci. And so I'm going to follow that treatment up to a point, and then I'm going to add some stuff that are my own thoughts on it in two places, in the middle and then at the end. So the idea is that as far as we know, all electrons would spin up are exactly the same. Now that may not be true, but as far as we know, it is. And all helium atoms in the ground state. Yeah, your question?
Yeah. When you say spin up, are you...
With respect to a particular axis.
Okay, but then there can be any direction, right?
Right. So the electron that spin up isn't identical to the electron that spin down.
But why couldn't you have like a spin on Y? If you're...
Yeah, all right. So electron spin Y is not the same as electron spin X.
Okay.
But you can rotate one into the other with a suitable magnetic field and so on and so forth. Big principle. Or at least you can have a beam, then you can select. Anyway. So all helium atoms in the ground state are identical. On the other hand, if you have a gas of helium at very high temperature, some of them are going to be in the excited state, and so they're not all going to be identical. In fact, that leads me to wonder about some of the applications of identical particles, especially to high temperature physics, because at high temperatures, the atoms and even the nuclei would be in different states, and so they're no longer identical particles, and whatever the statistics are they started with wouldn't apply at very high temperatures. Anyway, I don't know if anybody's pursued that theoretically or experimentally, but so the idea is that that we have particles that are identical, and the question is how to treat them. And let me describe, first of all, the kind of the problem. Let's think about electrons and and we can think of an electron 1 is spin up, and electron 2 is spin down, and that's one state. But then there's another state that's electron 1 spin down, electron 2 spin up. And since the particles are physically identical, these two states describe the same physics, really, and that's called exchange degeneracy. I don't know why the word degenerate and degeneracy is used so much in physics, at least in quantum physics, but it is. Okay. Now these states can form a space, alpha plus beta. And so that's a whole space of states, and that would be normalized as long as alpha squared plus beta squared is equal to 1. All right, and now let's consider the probability of measuring for this system, measuring both particles having spin in the x direction. Now the spin in the x direction, you'll remember, is 1 over root 2. Whoops, I of x instead of plus. For a single spin, it is plus, plus, minus. And we can actually, if you want, I can show you how to derive that. That is a rotation. If you take a plus in the z direction and you rotate the state about the y-axis in a right-handed way by 90 degrees, then it comes there. So this is equal to e to the minus I pi over 2 sigma over 2. It would be h bar, and then, in other words, h bar sigma over 2 divided by h bar, so the h bars cancel, times the state 1, 0, or effectively, well, yeah, I'm switching. These are two different notations here, of course. Plus is 1, 0, and minus is the same thing as 0, 1. And if you expand that, it would be cosine of pi over 4 minus I. This is sigma y. Minus I sigma y sine pi over 4. And so that should give that number. It's cosine of pi over 4 is, I guess, 1 over root 2, right? So this is 1 over root 2, 1 over root 2. And minus I gives us a minus 1 here and a plus 1 there, except for the 1 over root 2. And acting on that with 1, 0 gives us indeed exactly this state here. So is that, does anybody want to see any more detail? In any event, by the way, when you do this kind of rotation trick to get the eigenstates of sigma x or some other sigma, you get them to within an arbitrary phase because any eigenstate is only defined within an arbitrary phase. All right, so what is this probability? Well, the state would be 1 over root 2 the state 1 plus 1 minus direct product with 1 over root 2 2 plus 2 minus. And so now if we take the inner product of that with this state, what are we going to get? Well, we're going to get a 1/2, certainly, from the 1 over root 2's. And then, for example, we'll have, let me multiply this out. So it's actually, the state will be the state plus plus, plus minus plus, plus plus minus, whoops. Onto this alpha plus minus plus beta minus plus. So this would be the inner product, and this would give us 1/2 alpha plus beta, and so that would be the amplitude. So the probability of plus in the x direction, plus in the x direction would be a quarter alpha plus beta squared. And so that depends, in other words, upon the alpha and the beta. And as you then swing around this state, this space of degenerate, exchange degenerate states, all of which represent the same physical situation, you're going to get different probabilities for measuring both spins to be in the x direction. So in other words, the bottom line is that this exchange degeneracy isn't just some mathematical curiosity, it has statistical significance. Yeah.
How do you get 2 electrons in that state?
How do you get 2 electrons what?
In that state.
The state YY? Or XX, you mean?
Yeah, just in general.
Well, I guess, but I guess what you first of all, the way people did this originally was they talked about electrons attached to atoms, and in particular they were using silver in the very early experiments. By the way, you were right about neon. It was the inner shell of sodium is neon. So one way is to attach them to atoms and send the atoms through something like a Stern-Gerlach apparatus where the magnetic field points in the x direction. And on the other hand, we're talking about 2 electrons, and I'm not sure quite how we do this, but you'd have to pick up a suit. You might do it with 3 electrons, but it would, I understand those experiments are very hard. So anyway, let me beg off on how we do this. All right? I'm not quite sure how we do this, but it's at least plausible that we could do this or something equivalent. Does anybody have a good idea how to do it? Well, let's leave that aside. And of course, this exchange degeneracy presumably only gets worse when you have 3 particles or 4 particles or 100 particles. And of course, if you're dealing with something that's macroscopic, then you have something like Avogadro's number of particles. That's like 10 to the 24th. Somebody remember 10 to the 24th, 10 to the 26th, 10 to the 23rd, maybe. Anyway, big number. I think it's 16 to the 23rd, but I don't remember. All right, so the question is, how do we choose these alpha and beta? And Cohen-Janucci goes through he and his co-authors go through well, some of this is probably worthwhile because even though it's somewhat mathematical. First of all, if we have a state 1, particle 1 in the state, say, UI, and particle 2 in the state, say, UJ, and we call this then 1 UI, 2 UJ, like that. This thing is the same thing as 2 UJ, 1 UI, which is then, say, 2 UJ, comma, 1 UI. So that's the tensor product notation that most people use. Now we can define a permutation operator, P21, say, on 1 UI, 2 UJ, and what this does is it just turns this 1 into a 2 and the 2 into a 1, like that. And then we can rewrite that as 1uj, 2ui. So you can think of it as either changing the numbers or changing the state labels. So this is a permutation operator. And more generally, if we had, say, P21 on a state 1, R, and spin epsilon to R prime, epsilon prime, then this would be 2 R epsilon 1 R prime, epsilon prime, and that would be the same thing as 1 R prime, epsilon prime, 2 R epsilon. So we're labeling these particles by 1 and 2 so that we take the right inner products. Now, we can imagine state psi, for example, it would be a sum over epsilon, epsilon prime, integral d cubed r prime. Then we have psi of epsilon, epsilon prime of r and r prime. And then on 1 r epsilon 2 r prime epsilon prime. So this is sort of a general state in this space. And if we applied P21 on the state side, what we get would be this sum, the integral, and we get the same function, epsilon, epsilon prime, r prime, and then we get 2 r epsilon, 1 r prime, epsilon prime. And we could rewrite that as 1 r prime, epsilon prime, 2 r epsilon. And now, since r prime, epsilon, and epsilon prime are dummy variables, they don't care what we call them. We can change their names, so we can interchange epsilon and epsilon prime, r and r prime, and then we get some integral d cubed r prime, psi epsilon, epsilon prime, no, psi epsilon prime, epsilon, r prime, r, 1, r epsilon 2, r prime, epsilon prime. So you can think of this permutation operator either as acting, either permuting the number labels, or permuting the state labels, or changing the wave function so that psi epsilon, epsilon prime, r prime goes to psi epsilon prime, epsilon, r prime, r. So that's a mathematical manipulation that occurs often in physics, and it's worth thinking about for a moment, even apart from the subject of identical particles. Now, you can show rigorously that these operators, P21, is Hermitian. You can also show that obviously P21 squared is 1. And since it's Hermitian, then it is its own inverse, but its inverse is its adjoint, so it's also unitary. P21 adjoint is P21 inverse. So these transposition operators have all these properties. Okay. Now, we can then go on and define things. We can say that a state such that P21 on psi s is psi s. We can call this symmetric. And then we can say P1 on psi a minus psi a, and this would be anti-symmetric. And the operators that do this are S equal to 1/2, 1 plus P21. We're still in the space of two particles, two identical particles. And A can be 1/2, 1 minus P21. And you can see that these are both Hermitian. And you can show various other properties. I don't know if we need to show all of them, but what you can show in particular is that P21 on S side is equal to S side, and P21 on A side is equal to minus A side. So S and A are respectively operated as symmetrized or anti-symmetrized in arbitrary state. Okay, now, what about observables? Well, if you have, for example, an operator of some kind, then P21 on, say, an operator B1, P21 adjoint, so this is sort of a unitary transformation, although since the thing is Hermitian, it's somewhat artificial. That on one, say, the state particle 1 in the state UI, 2 in the state UJ, this would be P21, P of 1 on, now it would be, if I do both tricks, and this is 1 UJ, 2 UI, and then this would pull out, say, the eigenvalue Bj. This is the state J, so B is the value J. Particle 1 has the value Bj in this state. And then we have P21 on 1 Uj, 2 Ui, and then this flips it back, Bj becomes 1 Ui, 2 Uj. So that's that is to say then that P21 B1, P21 adjoint is effectively P2. And so I want to play various games with this, and what you can then say is that if you have an observable then that acts on, that's composed of, say, B1 and B2 in some way, and if that commutes with this, then you can say that the observable is symmetric. And in fact, that's what you expect. You expect that physical observables commute with all the permutation operators because particles are identical, and so it shouldn't matter whether a particle is particle 1 or particle 2 and so forth. And let me see, just an example, let me just throw an example. So the particles are identical, they have the same mass, they have the same charge, they have the same spin, and so a Hamiltonian might be P squared over 2m, P1 squared over 2m, plus P2 squared over 2m, and then plus maybe a repulsive potential R1 minus R2. And so what you see is this thing is entirely symmetric under the operation of this P21H. P21 adjoint is just H. And the same thing is remember we saw that the total angular momentum could be written as R1 cross P1 plus R2 cross P2. This thing is also symmetric under permutations. Notice, however, that R1 minus R2 is not symmetric under permutations. And that's why that doesn't occur in Hamiltonians. Instead, you always see the absent value as over here. All right, well, you can generalize this business of these permutation operators. Obviously, you can have, for example, if you have 3 objects, you can have P1, 2, 3. You can have P3, 1, 2, P2, 3, 1, P1, 2, 2, P2, these are the 6 elements of the permutation group on 3 objects. These are 6 permutation operators. And for example, P231 on the state 1 UY, 2 UJ, 3 UK is going to be 2 UI, 3 UJ, 1 UK, and then you can rewrite that as 1 UK, 2 UI, 3 UK. That's another way of writing it. These permutation operators form a group. The product of any 2 permutations is another permutation, obviously, because if you scramble once, you scramble twice, or then you scramble, which is what a permutation is. Now, what can you do about, what can you tell about these? It turns out that these 3 guys are odd. Why is that? Because they involve a single transposition. Okay, the first one involves a 3-2 transposition. The second one is a 1-2, and this is a 1-3 transposition. On the other hand, these guys are even, and that's because they involve no transpositions or 2 transpositions. And okay, so that's called parity of a permutation. The parity of a permutation is, I guess, -1 to the n, where n is the number of permutations. And this is something I forgot to mention. You can write any permutation as a product of transpositions. And so, for example, P1, 2, 3 is the product of 0 transpositions, so n is equal to 0. As I said, P132 is just P32. This guy is a little harder. P312 I'm guessing that it's P21 followed by P. It's something like this, but this may not be exactly right. This may be off by a sign. Or it may be wrong. But anyway, you can write it as a product of 2 transpositions. Let me see it. No, unfortunately. Yeah, all right. Yeah. All right. Yeah. Another way of writing it, so that this may or may not, what I wrote may or may not be right, but what certainly is true is that the product of P123 times P213. This one, as I said, was a transposition of 1 with 2, and this is a transposition of 2 with 3. And so you can write it this way. But these decompositions are not unique. It can also be written as P321, P132, and as various other things. And all of these permutation operators are unitary, but when you get away from transpositions, they're no longer Hermitian. And the next thing is just to think about this -1 to the n, I'm going to call epsilon. That's the parity of the permutation. So it's either positive or negative, +1 or -1. And remember, we had a symmetrizer over here, which was way back here, 1/2, 1 plus P21, 1/2, 1 minus P21. The generalization of that to n permutations is that S is 1 over n factorial. And n here is the number of objects.
sum over all the permutations, that permutation, and the anti-symmetrizer is 1 over n factorial, sum over all the permutations, the parity of the permutation times the permutation.
And so you can see that
S and A are Hermitian. And
okay, so all right, so those are useful. Let me now get to, I'm going to now deviate from continuity because I think I have a better way of describing these things. At least for the case of 2 spin 1/2 particles, or 2 spin 0 particles, 2 spin 1 particles. All right, let me say how I think of this symmetrization postulate, which is what we all know about, namely that you remove this, you use the symmetrization operator to remove the exchange degeneracy if your system, if your particles are bosons, identical bosons. You use A to remove the degeneracy if your particles are identical fermions. So if you have a state that's a state of fermions, you have P, you use A, the anti-symmetrizer, on the state of fermions, and this will be a physical state. So this is the physical state. And you use S on the side of boson, and this is again the physical state. And so in particular, in that example up there, you would have beta equal to alpha for bosons and beta equal to minus alpha for fermions. So for the example, you have alpha, well, since they're electrons, is the way I was thinking of it, you'd have beta equal to minus 1. And so you'd use this state, and then you normalize it to be 1 over root 2. So that's the application. Now let me say, give you a different way of thinking about it. And the idea is that you use the operators of the theory to make a state that doesn't distinguish between the particles or among the particles. And so if you have, for example, a state where particle 1 is at position x and spin up, and particle 2 is at position, say, minus x and spin down, then what you want to do is you want to produce this plus and now a physical operator that turns this into the other state. So in other words, the other operator, I'm going to call it U on 1x plus 2 minus x down. And let's think what that operator would be. The operator, if you had one particle here is x spin up, or let's do it simply with both spin up to start with, because this will be simpler. So one is at position x spin up, the other one is at position minus x spin up. Okay. Now what can you do to flip this around to the other kind? Well, you can do a rotation about the z-axis by angle pi. And so you say, you take this state
which I can only abbreviate it as x plus minus x plus e to the minus I pi, and it would then be sigma z over 2, acting on, and this would be sigma 1z plus sigma 2z, acting on the state x plus minus x plus. And so what this gives you is a factor of minus I. In both cases it would be, in other words, e to the minus I pi over 2 sigma 1z on 1 plus is going to be simply e to the minus I pi over 2 on 1 plus, and actually I lied, it's minus I, so this is minus I of the state 1 plus. On the other hand, e to the minus I pi over 2 sigma 2z on 2 plus is then the same thing, e to the minus I pi over 2 plus, and on the other, I left out the x, so this 1 is at x, and we, instead of using sigma, we also use L, so it's minus I pi Lx, LZ plus L1z plus L2z. So we're rotating the whole thing, so this should be stated as 1x plus goes to, I was just doing the spin part here, so it's 1 plus times e to the minus I pi L1z on x, and altogether then this gives us minus I minus x, 1 in the state minus x plus. And this, if we do the same thing on this one with minus I pi L2z, and this is the state 2 minus x plus, then this will give us 2x plus. So in other words, which is to say minus I 2x plus. Okay? The result of this then is that this state is 1x plus 2 minus x minus plus. And now minus I times minus I is minus 1 minus 1 minus x plus 2x plus. Okay? So in other words, if you prepare the state in a symmetrical way using a physical operator, then the fact that this is spin 1/2 gives you the correct sign here. Okay. So you might say, well, what about the case plus minus? Right? Or obviously the case minus minus works the same way. With the case minus minus, you just have two factors of I, and you still get the minus sign. So you get as your physical state this, although of course you have to normalize it correctly with a 1 over square root of 2. So the normalized state is 1 over root 2 times x plus minus x plus minus x plus x plus. So now we can think about, well, suppose these things would spin 0 particles. Well, if they would spin 0 particles, then we wouldn't need the spin operator at all. We'd just use the orbital angular momentum to generate the rotation. And in that case, we would have
x minus x plus this u on x minus x, and this would just give us x minus x plus minus x, which we then normalize to 1 over 2 x minus x plus minus x. Okay. Now the tricky case is, suppose we started with, say, a plus here and a minus there. All right, so let's think about what the physical rotation has to be there. So this is the one that I started with and changed. So let's make it x plus minus x minus. Okay. So now, as the rotation about the z-axis won't work because it will take the spin plus over here. Would that work?
Couldn't you do that and then flip the spin of the operator?
Let's see. Let me just. What we have here is x plus minus x minus, and what we know we want as our answer. Luckily, we know what the answer is. We want minus x minus, comma, x plus. So that's the thing that we want, divided by the square root of 2. And so if we rotated this around by z, it wouldn't work. And you were going to suggest what?
Couldn't you rotate it and then do it about y? Or no?
That may work. That may work. But let me tell you, I've done this problem before. So I'll tell you what the answer is. Suppose you rotate about the y-axis. If you rotate about the y-axis now, you're going to bring minus x minus. See, this spin is going to be down. And then when you rotate, so it's going to look like this, it's down. Now when you rotate it about the y-axis, it's going to be up. So let's just check that. E to the, and let's say it's a right-handed rotation. E to the minus I pi sigma y over 2. Let's just see what this is. Well, this is cosine pi minus I sigma y sine pi. And of course I got it wrong. It's pi over 2. Now cosine pi over 2 is 0. Sine pi over 2 is 1. So this is minus I sigma y. And this is just 0 minus 1, 1, 0. So in fact, this is, we have the following. We have e to the minus I pi, I'll write it differently, sy over h bar on the state plus, well, it would be effectively 0, 1, minus 1, 0 on 1, 0. And this would just give us 0, 1, which is the state minus. On the other hand, e to the minus I pi sy over h bar on minus then would be 0, minus 1, 1, 0 on 0, 1. And this would be minus 1, 0, which is minus plus. So this is a minus sign. Remember, we got a minus sign over here because we had two factors of I or minus I. Over here, we get a minus sign because of the rotation about the y-axis. If we get it for one of the states, but not, we get it for the minus state, but not for the positive state. So the orbital angular momentum, so in other words, we act on the state e to the minus I pi jy on the state x plus minus x minus And that gives us then minus x minus x, oops, x plus, which is what we want. And so the rule then that you take the original state, x plus minus x minus, and add this unitary transformation, this physical transformation, using the operators of the theory, x plus, I suppose. This gives us then x plus minus x minus minus x minus x plus, and if we normalize it, we get 1 over root 2. So in other words, one way of stating this rule for the symmetry of identical particles is to say you simply take the state and then you do a physical operation that interchanges the two particles, and that gives you the correct sign and permutation. And of course, if these were bosons, then the sign wouldn't have occurred if they were spin 0. If they're spin 1, so let me discuss spin 1 for a second. But there must be a question here. I like this way of doing this. I don't know. Because you see, the normal way when you discuss this in the text, it's just written as a postulate. Although in quantum field theory you can derive it in some different, but in ways that aren't very much different from this. Okay, suppose we have spin 1. And now we have, again, suppose x, and now we have m, minus x, m. Or just to make things concrete, let's make this a spin 1 particle. Let's just say it's a massive spin 1 particle, so we don't have to fool around with the fact that the mass of this particle only has 2 polarizations. Okay, so what would the rule be here? It would be this plus a unitary transformation on x1 minus x1, and the transformation would just be a rotation about the z-axis. So this would be x1 minus x1 plus e to the minus I pi jz on x1 minus x1. Well, now the orbital angular part is just going to turn x into minus x and minus x into x because it's a rotation about the z-axis. So we've got particles originally here, minus x1, rotates them like that. The rotation, on the other hand, about the z-axis is going to give an e to the minus I pi for both of these guys. But that's a minus 1 for both of these guys. But minus 1 times minus 1 is 1. And so the answer is that this is equal to x1 minus x1 plus minus x1 x1. And so then we take this and divide by 2. So for bosons, you see, because this, in other words, e to the minus I pi, and I'll just write s sub z on 1 is just e to the minus I pi 1, which is minus 1. But this occurs on both this one and that one. And so you get 2 factors of minus 1. Clearly, if they're both spin down, you get plus 1 twice. And so plus 1 times plus 1 is plus 1. And on the other hand, you have plus minus, well then you need to do the trick with the rotation about the y-axis. There's also the possibility, though, of if it's a massive particle, spin 1, you can have 0, 0, and then you just rotate about z, and there's no problem. So,
is that spin 0 like a linear combination of the 1 and a minus 1?
no. What we've got here is we've got 1, 0, 0,
Okay.
0, 1, 0, and 0, 0, 1. So I'm using
So they're
that
all
basic.
like in their own subspace or something, right?
Yeah, I guess. I'm not sure what you mean by that, but here I'm talking about a spin 1 particle. So in other words, J squared on Jm here is h bar squared times 1 times 2 times Jm, and J3 or Jz on Jm is h bar m Jn, and here m is less than or equal to j, greater than or equal to minus j, so it runs from minus 1 to 1. Okay. Well, I think one can work these out for other cases, such as 1, 0, and plus and minus, and so forth. The plus 1 and minus 1 can work the same way as doing this rotation about the y-axis, and that would again turn something that was, say, spin down into something that was spin up, and something that was spin up into spin down. The question is, what are the factors? And for that, we need the rotation matrix in the basis in which Jz is diagonal, and I forget what that is. Maybe I'll assign that as a homework problem. One of the reasons, by the way, why I went through this is I think it's a nice review of spin, as well as I think it's a partial explanation of why it is that you use the anti-symmetrizer for fermions and the symmetrizer for bosons. All right, so let me erase some more of this board and then continue with Tanucci's treatment. I believe that one can generalize this completely, but I haven't done it. Obviously, there are infinitely many cases, and to do each of them by hand is.
Is there any sort of insight as to why fermions behave the way?
Well, I think you're getting it from this.
I thought we postulated that.
Well, no, that's the standard thing people do. What I'm saying you should do is you postulate that you take a linear combination of, in the case of two particles, the state and then an operator acting on the state that permutes the two particles. And that physical operator on the first state will give you a minus sign or a plus sign. That's the idea. So that's what I'm saying is I don't know if it's in the literature. Might be somewhere. I've never seen it. Anyway, that's how to remove the exchange from Confederacy, and it associates. I mean, it gives you one rule, and then the physics of the mathematics of the spin then gives you the correct association between fermions and bosons. All right, let me get back to Tanucci's treatment, which is pretty good. I'm trying branch love to be precise, and that's often an advantage. All right, so, of course, let me just say then, the generalization of this to arbitrary, to n particles, is that what you would do is you would start with your states, for example, 1, u, I, 2, u, j. Let me just do 3 particles, u, k. And then you add all the other cases, which would be, or equivalently, a better way of saying it, whoops, I shouldn't have done that. 3uk, you do a sum of these unitary operators. The unitary operators to physically implement the permutation alpha, and then normalize by 1 over, I think it's 1 over square root of n factorial, but I don't know. Anyway, you want to normalize it somehow. And so this physical operator will do the permutation, but when it does the permutation physically, it gives you the, it would, I believe, give you the correct sign. And so you get alternating signs for, in other words, it gives you the same rule as the rule up there. But as I say, actually deriving that for every case is another matter. Now, suppose we have identical bosons. So then, what we're left with is, if we had bosons, this operator U would always give the plus sign. And so you'd have just a linear combination of all the different permuted states. And what you'd say then is that the state effectively would have then, let us say, N1 states in other words, you could rewrite it as 1U1, 2U1, up to N1. Suppose the original state you started with was this. And then you'd have, well, you really have N1 plus 1, comma, N1 plus N2. This one in U2, all these in U2, and so forth. And you say then that there were N1 bosons in state U1, N2 boson in state U2, and you write that in this occupation number representation. So it would be N1 bosons in state 1, N2 in state 2, N3 in state 3. And this particular thing then would be, you could either write it in this way or you could write it in the mathematical way, but it would be a sum over all the, either all the permutations on the original state 1, U1 up to this huge number. Again, you have to normalize it. Or, I guess you could write it as with these physical unitary operators. For the case of fermions, what's the maximum value of n, of these N1 or N2? All right, well, let's think about it. The point is that you see, suppose you wanted to put both particles at point 1 at the same place with the same spin. Then what you would have would be x plus, say, x plus. You'd have that plus this unitary operator on x plus. But that would give you this x plus minus x plus, and that's 0. So you can never have two fermions in the same state.
And so that's a result of
Huh?
that's just a result of being in identical, or
Being identical fermions.
the Pauli exclusion principle.
That's the Pauli exclusion principle. Another way of saying it is, the conventional way of saying it would be that you use your anti-symmetrizer on the state side, and this would be a sum then of P alpha times epsilon alpha on the state. And if you permuted two particles that were in the same state, then you wouldn't change the state, but you'd have a minus sign due to the parity of the permutation, and that would give you 0. Now, in particular, these observables, as I said, because the particles are identical, the observables are symmetric under permutations of the particles and of the particle numbers. And so in the time evolution, if you start out with a state that is completely symmetric or completely anti-symmetric, as you must for n-identical bosons or fermions, the thing stays symmetric because, let's see, maybe I should do a sort of description of it.
These are indistinguishable and identical, right?
Indistinguishable and identical is the same. We use it for the same, it means the same thing in physics.
Okay.
Now, whether that's the best way of doing it, I don't know. Okay, suppose we have the symmetrizer e to the minus IHT on some state psi. And suppose this state psi was already symmetrized. So in other words, is this state equal to e to the minus IHT psi? And in fact, what I want to say is I want to put another S there. And in fact, it is because, first of all, the symmetrizer commutes with the Hamiltonian, and that's because the symmetrizer is the sum of all the permutation operators, apart from an overall constant. And the permutation operators commute with the Hamiltonian. So if we start with a symmetrized state, then we can move the S through, and so this is equal to e to the minus IHT. Actually, I didn't want to write that. I wanted to write this. It's e to the IST, S squared psi. But now S squared is equal to S, and so let's just see why that's the case. S squared is 1 over n factorial, sum P alpha, 1 over n factorial, sum P, say, beta. And so this gives us 1 over n factorial squared sum P alpha P beta. And actually, a better way of saying it is that the symmetrizer, the symmetrizer squared is 1. We've essentially seen that. We have seen it over here for the case of Well, maybe I should. Let me just show you this in the case of two particles, where it's easy to see that it's true. It's a little bit less easy to see that it's true in the general case. So S squared here is 1/2 1 plus P21, 1/2 1 plus P21, and this gives us 1/4. 1 times 1 is 1. P21 times P21 is 1. And then we get 2 P21. And so this is 1/2 1 plus P21, which is S. So here S squared is equal to S. Over here, this P alpha P beta is another permutation. But these things form a group, and what you wind up doing here is you get all the permutations. You get each permutation. In this product over alpha and beta, you get each permutation n factorial times. So in other words, 1 over n factorial squared times the sum over gamma, p gamma, but this p gamma, and you get p gamma n factorial times. And so altogether this is S. So that means that this is e to the minus I HT S on the side. So in other words, we start out with, if we have identical bosons, the physical state is S times psi, appropriately normalized. After a time, we're asking, is it the same, is it still a symmetrized state? And indeed it is, because what we've seen is that S on the state is equal to the original state. And so it's still a symmetric state. And on the other hand, we can do the same thing for the anti-symmetrizer. I should have done another blackboard rather than erase this. So let's recall what the thing is for two particles. The anti-symmetrizer is 1/2 n minus P21. A squared is 1/4 1 minus P21 squared. That's 1/4 1 minus P21 squared is 1, and then minus 2 P21. So this is A again. And more generally, if A is 1 over n factorial, the sum over permutations, parity of the permutation times the permutation, and A squared is 1 over n factorial squared, the sum over alpha beta, epsilon alpha, epsilon beta, p alpha beta. Now, this will be, no, p alpha times p beta, sorry. Now, the product, this is a permutation that has a certain number of transpositions. And what's unique is not the number of transpositions, but whether that number is even or odd. And so, suppose we say that the first one has 4 transpositions, the second one 5 transpositions. Then the product will have 9 transpositions. And equivalently, it will have an odd number of transpositions. And of course, even times odd is odd, or plus times minus 1 is minus 1. So this gives you the same thing as A. And so if you start out with a state psi of identical fermions, and then you remove this exchange degeneracy by operating with A psi, you advance the thing in time, and then you test it with the symmetrizer. What you're going to get is e to the minus I HT A squared psi, and you're going to get then e to the minus I HT A side. So the anti-symmetrizer on the state has no effect, which means that the state is already anti-symmetric. Do I really have? Right, that's right. It's the notice that that's just a consequence of a squared equal to a. On the other hand, that doesn't mean that a permutation on the state, a transposition on the state, will give a minus sign. All right, I guess that's. Are there any questions? Actually, you asked several questions, and I didn't give you any chocolate.
I'll take mine in a lump sum at the end.
All right, let me go.
I have a question. Okay. If I
Oh,
have,
and I forgot to give these things out. Does anybody want these?
okay, if I have an electron here that's spin up, and another one here that's spin up, I can tell them apart, right? Since they're
because they say macroscopically apart. Yeah.
Okay, so if
Oh, you're
I put them in a well now and cool it, and they get closer and closer, when can I no longer distinguish them?
Well, it's the answer that is normally given is when the wave functions overlap, then you have to take into account that they're identical particles and anti-symmetrize them. When the wave functions don't overlap, you don't really need to consider them to be identical particles. And in fact, you put your finger on it. It's when you say that, I mean, you started out by saying you have an electron here and an electron there, you can distinguish them. You can distinguish them by their positions. So they're distinguished by their positions. If they're distinguished by their positions, then effectively they're distinguishable. But once the wave functions overlap, they're no longer distinguishable.
Okay, so if we bring them in close and they still have the same spins, and now their wave functions are going to cancel, because, or is one of them going to flip?
The wave function has to be anti-symmetric in space if it's symmetric in spin. So let's try to think about what that means.
Well, I'm saying, like, you have the example right there where you have.
Let me just do it. It's phi of x1 psi of x2 minus phi of x2 psi of x1 times some normalization. Okay? So this is 0 when x1 is equal to x2. But it doesn't mean.
But when you say it's 0, does that mean that the wave function is canceling? But you
Yeah,
still
the wave
have
function is actually 0 when the two particles have the same coordinates.
But you still have the mass energy for two particles?
Huh?
But you'd still have the mass energy for those two particles?
Oh, for sure, yeah, there's still two electrons. What cancels is the wave function when, in other words, the wave function for the two particles would be of this form. So you have some omega of x1, x2 look like that.
I'm still a little confused. I mean, like, this says that if we have two electrons spin up and we get them close enough together, their wave functions will cancel.
Right, so you can't get them, the probability of them being at the same spot is 0.
Okay.
But they can be close. And let me just emphasize something. Suppose you're talking about two hydrogen atoms.
Okay.
And what you conventionally do in a simple approximation due to Born and Oppenheimer is you treat the two protons, since they're 2,000 times heavier, as classical objects, and you treat the two electrons quantum mechanically. And you say that these two things are a fixed classical distance r apart. Well, then you know you have to have an antisymmetric wave function with two electrons. But you have two choices. You can say that it's symmetric in spin and antisymmetric in space, or antisymmetric in spin and symmetric in space. And it turns out the correct answer for the ground state of hydrogen is symmetric in space and antisymmetric in spin. So in this case, they kind of hug each other in the center like that, but the spin I don't want to say wave function, but the spin state vector is antisymmetric in spin. So it's plus minus, 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 plus. That's the spin part. And the space part is symmetric. Symmetric meaning, of course, that it's this times phi of x1 psi of x2 plus psi of x1 phi of x2. So this thing multiplies that thing.
So when they're both together there, that...
Yeah, the electrons, in the case of a hydrogen molecule, and this is true for most of these molecules, general covalent bond, is the electrons crowd together as if they were bosons, but the spin is antisymmetric. So it's a spin singlet, but the electrons are crowding together. And notice how this makes the thing a molecule. You have a big negative charge here, and then you have a plus charge here and a plus charge here. The two positive charges are attracted to the electron cloud in the middle.
So what would it look like if it were, say
the opposite?
Antisymmetric in space?
Well, then you'd have...
Is that like one... So I've never really had a good definition for this space symmetry, or at least a picture.
Well, it might look like this. You have this one nucleus here, one nucleus there, and this guy would look sort of like this. Would look kind of like that.
Okay. So they crowd.
So when you say
okay.
when you go to the point in the middle, you ask what's the probability of the two electrons being in the middle? It's 0.
Okay.
And this gives you actually a higher energy state. I think it's a positive energy in fact. I would confess to you that when I first did I was playing around calculating the hydrogen atom, the hydrogen molecule. I thought that it was antisymmetric in space and symmetric in spin. And I computed what the energy would be using, I guess, a variational method. And I kept getting an energy that was too high. And then finally, it's sort of like, the Sherlock Holmes and Watson, when you examined every reasonable case, choose an unreasonable case. I chose the opposite, and then it worked out. Anyway. Any more questions? All right, well, we have spring break coming up next week, so there's no class. And then we'll start classes normally when the spring break is over. But then we have 2 makeup classes, and we have to think about what we're going to do about them. You might as well turn the thing off.